All right, let's look at doing derivatives of the trigonometric functions. We know how to do the antiderivatives of trigonometric functions. We know how to do the integral of things like sine, of sine or cosine. We also know how to do things that were answers to the derivative problems from earlier, right? Things like this, or things like this, negative cosecant squared x, or negative cosecant x tangent x. If we were doing the antiderivative of these, we know that sine would have come from cosine. I just might have to adjust the negative. I could get cosine. If I were integrating, I could get cosine by doing the derivative of sine. Okay, secant squared comes from tangent. This guy comes from secant. This guy comes from cotangent. That comes from cosecant. All right, so I know those rules, and so far that's the only thing you can do the antiderivative of, are things that came from, that were answers to derivative problems we did earlier. But if you just have tangent or cotangent or secant or cosecant, not squared, but just secant or cosecant by themselves, you don't have a strategy yet for that until section 5.7. All right, so let's look at 33 on this one, and then we'll do one of these two because they're very similar. So if I were doing 33, I could have memorized the rule, or I could figure it out. I would have done this one by thinking about how cotangent is cosine over sine. Right? So this is what I've got. And then I notice how the denominator is sine, and it's sine of something, and this whole denominator is just to the first power. And I'm thinking how the derivative of sine is cosine. So I'm thinking this part right here would be what I get when I do the derivative of the denominator. So that makes me think about rewriting it or thinking about it this way. Sine of theta over 3 times cosine theta over 3 d theta. Okay. And then this looks like an ln problem. So I kind of know the gist of what I'm going to do. If you are good at pattern recognition, you might be able to go from there and get the ln of sine u and so on and be done. But you do have to adjust things, the constant, a little bit because of the right there having not just a theta, having theta over 3. So you might use the u to think about that. So the derivative of this with respect to theta would be du would be 1/3 d theta. So d theta could be replaced with 3 du, couldn't it? Okay. So in terms of u, I could have 1 over u, 1 over sine u, excuse me, that's a big faux pas, 1 over sine u, right there, times cosine u, and then in place of the d theta, I'm going to put 3 du. Okay. So I'm going to need to integrate 3, 1 over sine u, cosine u, du. So I'm just moving that constant out in front like we normally have it. Then I'm thinking about this and realizing, okay, the derivative of 1 over something comes from ln. So this is ln of the absolute value of sine u. Okay. That would give me 1 over sine u. And then the derivative of the inside would be cosine u. So I like the look of this, okay? The constant would just be brought down in front. I would throw a plus c at the end, and then I would put the theta over 3 back in and be done. And that would be my final answer, okay? All right, we're going to do another one of these. Why don't we go ahead and look at 35, do the cosecant of, let me get to my slideshow screen. Let's do the cosecant of 2x dx. We're going to do it in a similar way. All right, so I'm going to erase that. Wish I had a duplicate, duplicated that. I'm just going to go ahead and erase that previous problem. And then we'll look at 35. Okay. So when I'm thinking about that 35, if I have memorized the rule for that, then I would just use the rule. Okay. So the rule for cosecant involves just doing a natural log of cosecant u plus cotangent u with a negative out in front. I'm going to kind of show you where that came from. Okay. So the 2, let me do it using the rule. You would need to think about u equaling 2x. So du would be 2 dx. Okay. So I could rewrite this expression in terms of x's. So what I'm trying to integrate, I'm going to go up here to do it, would be the integral of cosecant u now. And in place of dx, I'm going to put 1/2 du. Okay, I'm going to put the 1/2 du in. So I'm going to have a 1/2 cosecant u du that I'm trying to integrate. So here's where, if you know the rule for integrating cosecant u du is that would be negative ln cosecant u plus cotangent u plus c, and then there was a 1/2 we need to carry along. So we'll clean it up. We'll do negative 1/2, and then we'll do natural log of cosecant, and we'll put the 2x back in place of the u. Okay. And then that would be our answer. Okay. All right. So I showed you where that cosecant one came from in the video that I did earlier. So you could go back and look that up if you wanted to, or I'll just show you real quick where that came from here. So let's say we were trying to integrate cosecant u du. Seems like a weird thing to do. And a lot of times, if you remember the process for proving what it turns out to be, then you basically already know, you already know the rule for the most part. So what you do is you multiply the cosecant u by cosecant u plus cotangent u. Okay. And to start with, if you don't know for sure what it is, this might be all you think you need. Okay. All right. And then what happens is I notice how it's always okay to multiply the top and the bottom by the same thing. How that would become cosecant squared u. This would become cosecant u cotangent u. And this denominator would remain cosecant u plus cotangent u. Okay. So what's good about this is it gives me something that has to do with cotangent, and it gives me something that is related to the derivative of cosecant. I need an extra c in there. Cosecant. All right. So where all that comes from, or why that works, is I'm looking at this denominator as being basically to the first power. So I'm thinking about it like this, like 1 over cosecant u plus cotangent u. Then off to the side, I would have the cosecant squared u plus cosecant u cotangent u du. Okay. And I wrote it that way because the derivative of this right here is, for the most part, what you see over there, except wouldn't you need a negative, like the derivative of cosecant u? Remember how that was negative cosecant squared u? And the derivative of I said it backwards. The derivative of cosecant u would be cosecant u cotangent u, except it would need a negative. And the derivative of cotangent u would be the cosecant squared u, but you would need a negative. So this almost works, but I would need a negative on these. These would need to be negatives. Okay. All right. So what that means is I need to get a negative on those somehow. So what I'm going to do is throw a negative on this down here and throw a negative on this part up here. And I'm going to go ahead and distribute that negative. Then I would have a negative there, and this would be a negative. Okay. All right. So then what would happen is I would have the rule being, so this would be a negative, with a negative here also. So this would wind up being a negative because the constant can just be brought down, and then natural log of the cosecant u plus cotangent u, and then plus c. And that's where the rule comes from. So I've already showed you the rule. You either memorize it or you know how to derive it. Okay. And then what happens back here is you can use the u substitution to figure out what the constant is, or you can think about how, when you do the derivative, how you're going to do 1 over the part you have inside here. Okay. And then you have to take also the derivative of the inside function. And so that's going to wind up being the 2. And so you need to somehow be knocking out that when you do the derivative of that inside function. Okay. So our final answer should be -1/2 natural log of the absolute value of cosecant 2x plus cotangent 2x plus c.